Okay, so we will consider an interesting application of this Ramsey theory. So maybe I will start with some story that in 1932, there was a group of talented students in Hungary, and there was this girl called Esther Klein. And then she suggested a problem to her friend. And later, two students there, one is Erdish and then the other is Zechariah. They suggested several proofs of this problem. She suggested the problem and then they answered it. And after that, 4 years after that, this Zechariah and Klein, they got married. So I just named this theorem, which answers her problem, as a happy end theorem. So this is happy end theorem. So what is it about? This is proved by Erlich and Zechariah. So for natural number m, they show that there exists an integer n, which depending on this m, such that every set of n points in the plane. So if you put the points in the plane, such that no 3 points are on the line, but they are collinear, meaning that the 3 of them are on the same line. If that doesn't happen, in other words, those points are in general position, then there must be an m subset. So set of m points, they form a convex n. For example, if you have these, then no matter how you put many points, you can always find this convex cone of certain size. And then if you put many enough, then you can always find 10 points, which forms a convex 10 cone, or 20 cone. As long as you put sufficiently many points, then you can always find it. So, as I mentioned, there are several proofs of this, but we will use Ramsey theorem to prove it. Let's prove first claim. So, among any 5 points in the plane in which no 3 of them are collinear, always 4 of them determines a convex quadrilateral. That's 4 good. Proof is not difficult. So what you do is you have these points and then you take the convex part. which is the smallest convex set containing all of them, then this convex hull is either pentagon or quadrilateral or triangle. If this is either pentagon or quadrilateral, you just take this four or this four, and that gives you a convex quadrilateral. So we are done. So in remaining cases where this convex hull is triangle, then what you do is you have a triangle and then 2 points inside. Then you take a line passing through these 2 points. Once you draw this, you have 2 sides. One side contains 1 point and then the other contains 2 points. Then you choose these 4 points and then must form a convex quadrilateral. So that proves this claim. I'm not gonna write it down. And second claim is that if every all subset of m points, you have m points and then you choose any 4 of them, say in the plane, of course, they form a convex quadrilateral. Then the m points form a convex angle. So this allows us to check whether m points form a convex angle or not using its local property. So how do we prove it? You take contrapositive. If you have m points and then they don't form a convex angle, then what happens? You consider its convex hull. Then this is a T-gon with T smaller than m, convex T-gon. And then that means m minus T points are inside. And what you do? You take 1 point and then you triangulate them. I mean, it doesn't have to be 1 point. You triangulate. You add a straight line until you get the weak triangulation. So everything inside is partitioned into triangle. And then, because no 3 points are on the same line, that means one of them is contained in this triangle. Then what happens? You take these 4 points, then though that form subset does not form a convex quadrilateral. So you prove the contrapositive. If this is not true, then this is not true. That means that this claim is proved. Okay, with these 2 claims, what you can do is that let capital N as a Ramsey number of M by Paul uniformity. So you consider Paul uniform hypergraph, and then you consider this number. This number must exist, as we prove. And then what? Now we given its n points in the plane. We give a coloring. Color each all subset by its convexity, meaning that we color with red if it determines convex quadrilateral, and blue it's not. Then what? What does this first one say? If you have 5 points in the plane, then 4 of them must be colored by red. So by claim 1, we have no blue homogeneous 5 set discoloring. But by the definition of this N that imply by Ramsey theorem, there must be M points whose 4 subsets are all red. But what the second claim says that when every 4 subset forms a convex quadrilateral, then they form a convex angle. Hence, this N exists and its most are M5 semicolon 4. Okay, this gives you this theorem. So this is an interesting application of the Ramsey theorem. And then, we can ask that quantitatively, is it the best bound? Can we prove a better bound? LG and Jacqueline. They proved that this number is at least 2 to the n minus 2 plus 1, and then n most 2n minus 4 should n minus 2 plus 1. So again, this is n most 4 to the n. In 2017, Andrew Sook proved that the n of m is n most 2 to the n plus some constant times n to the 2 over 3 log n. So which is smaller than 2 to the 1 plus epsilon n, or arbitrary epsilon. So this kind of shows that this lower bound and upper bound are, asymptotically same once you take the log. So, this is best known inequality regarding this number. This is this set. Okay, so this was one interesting application of the Ramsey theorem. And as I mentioned, we want to discuss about the lower bound of this Ramsey number. But before that, let's mention one more generalization of this. So here we consider the Ramsey number in a sense that for graph case, we find the either red complete graph or blue complete graph of size P and Q. So that was how RPQ was defined. But instead of this complete graph, we can ask the same question with a more general graph. Let's say for graphs G1 to GK, we say the graph Ramsey number, or simply Ramsey number, R G1 to GK is the smallest integer n such that every k coloring of the edges of complete graph on n vertices must contain a copy of GI in color I or some I. When this GI is all same, this is G for all I. We simply write R sub K of G, which is R of P1 to Pk, where all of them are same with G. Note that if say Pi is the number of vertices in Gi, then what? Gi is a subgraph of complete graph on Pi vertices. So this P1 to Gk must exist. It's a most Ramsey number of P1 to Pk. And so as seen before, the gap here is, when you take log, it's almost lower bound and upper bound are similar, but as a number between this and this, there are quite a multiplicative gap. And then we will see later that this upper bound and then best known lower bound has a large gap, the exponential gap. So in general, the lower bound and upper bound for Ramsey numbers are quite far. But there are very small number of cases that we know the value of Ramsey number in a precise way. So one of them is this. So if T is on M vertex 3, then what happened? The Ramsey number of T, Kn is exactly n minus 1 times n minus 1 plus 1. So we know this. If you consider two graphs, and then one of them is complete graph, and then the other one is 3, and we have this. And first, for lower bound, how do we do it? What do we have to do? We have to find the coloring on this many numbers without 1, which lacks over red 3t, and then blue Kn. Then what? You consider disjoint union of Kn minus 1, all of them colored with red. How many of them? N minus 1 copy. And then everything between, you color with blue. Then what happened? This T is M vertex 3, so there are no red T. Because, each connected component in the red graph has almost n minus 1 vertices. And then this is n minus 1 part, so every blue graph here is n minus 1 chromatic. So there is no n chromatic blue graph here, but Kn is n chromatic. So you cannot find blue Kn here. So this shows that this has to be strictly bigger than n minus 1 times n minus 1, which is what we wanted. And let's consider the upper bound. For upper bound, let's remind the fact that any graph with linear degree at least m minus 1 contains any 3 T with m edges as a subgraph. This is easy to prove using induction. You take a T and then you delete an H, and you delete the leaf, and then you find the T minus leaf L, and then you embed L at the last moment. And then at that moment, you have enough minimum degree. So you see where this neighbor of this leaf is embedded, and then it has many leaves. One of them is not taken. It has many neighbors. One of them is not taken, then you put the leaf there. So this is well-known fact. So now we prove the upper one. We use induction on N. The base case. N is 1, it's easy. N is 1, but when N is 1, K1 is just one vertex. As K1 has one vertex, no edge, so it's trivial. For any bigger, we consider two coloring of the edges of K n-1 times n-1 plus 1. If a vertex, a particular vertex X has more than n-1 times n-2 edges, neighbors, or lower blue edges, then what the induction hypothesis again give you, this is like what we did in the proof of Ramsey theorem. It's guaranteed either red T or a blue Kn-1. And together with X, we either get red T or blue Kn. So if this X has large blue neighborhood, then in here you either find red T or blue Kn-1, but together with X you get the blue Kn. So that means it doesn't have a large blue neighborhood. So otherwise, every vertex has at most n-1 times n-2 incident blue edges, and at least n-1 incident red edges. Because, because of the number of vertices here. Now, what? Together with this, now, there is a red T because the red line has minimum degree. It is n-1. So, it proves what we want. Okay, so we learned about an application of this Ramsey theorem, and then we generalize this Ramsey theorem for general graph. And next time we will start learning about probabilistic method, and then we use this to find the lower bound on this diagonal Ramsey number. So yeah, that's our plan. I will do that from next video. Thank you for listening. I will see you in the next video.